parents know anything about PhD.
Oh, really? I didn't say they know something about it, so they want to watch. Hey, Lam, I can see you're present. I'll remember this.
Is Jimmy coming?
Yeah. Okay. Has to be really serious, right? No humor or. Denny said he'll join via Zoom. Hey, Aman, I can see you. Oh. Wait, am I? Yeah. I've got one. Chong. Chong and I go way back. Yeah. Hey, Kevin. Hey, Jenny, I can see ya.
Hello, Jenny. Yes.
Oh no, there's a lot of people. Hey. Hey. Oh, hey.
What do you think?
He lives right there, you know, Jimmy's office. Hey, Jimmy. Nah. I think we can start because
I'll give you one minute.
Wait, now I can't control the screen. Oh.
Then driving.
Yeah.
Hey, Danny, you're not allowed to zoom and drive, no?
I think he's muted.
Yeah, I know.
Yeah, that's why I'm not pressing the button. Just go ahead.
Video it and are you ready?
Yep.
All right.
Good. I'll just
Welcome everyone to Tony's completion seminar. Tony actually did a PhD with Jimmy and myself, and I guess a lot of this Jimmy's work and Jimmy's mentorship have carried Tony very, very far in his PhD. I would just want to say that Tony did his undergrad master's capstone project with me, right?
I did.
And so he finished the project. I thought I'd never see Tony again. But then I think you were I don't know. I was surprised to get a letter from email from you wanting to do a PhD. And I initially checked that it was actually with me and not with someone else.
Yeah.
So he did come back and he has done a PhD, and in this completion seminar on particle-induced modulation and dispersion of inertial particles in the form.
Yep. Okay, so I've got to. Okay, thanks, Andrew. And I actually emailed Andrew, but he didn't reply for a whole week. Yeah, he actually didn't, and I thought, oh, that ship sailed. He's not going to reply. Anyway, so I'm going to kind of motivate you today on why you might be interested in particle-laden flows. I would argue to the single-phase flow people in this room that there's no such thing as a single-phase flow in the real world. They are all, one way or another, particle-laden flows. So in buoyant plumes, such as fires, you actually have fly ash in that buoyant plume. When wind goes over plains, it entrains dust. Pandemic, if you've ever lived through a pandemic, you'll know that those coughs and sneezes are actually laden with droplets. And actually, in the formation of the planet you're standing on right now, that came from a particle-laden flow. So hot air was, hot gases were being moved around, and planets formed in those protoplanetary disk flows. So, looking at the iceberg of my PhD being the Titanic approaching it, underneath there's a lot of maths. There's a lot of maths, but we're not going to focus on that today. But no, it's there. We're going to focus on the pretty pictures, right? So, first thing we're going to talk about before we move on to particle-laden flows is single-phase flows. I think someone's just come. Sorry. I'm just expecting Katie. So.
Oh, are you? Oh.
Yeah. Yeah. Oh, hey, bud. Yeah. So before we move on to particle-laden flows, let's commence with single-phase flows. So we did some numerical work here on spectral element methods. And spectral element methods feature these high-order polynomials where you use Lagrange interpolants. I'm just going to try and move that. So Lagrange interpolants are kind of fancy because for 64 grid points on an analytic function, you can actually recover that function really well. And that's different to the linear interpolants that you see on screen here, where you'd get a significant error in the result. You might be thinking, why now? Spectral element methods have been around since the 80s, but given their high order polynomials that feature, you get these dense packings in the matrices in your linear algebra systems, and that commands a high memory footprint. And it's only in the last 10 years or so that this class of method is suitable for turbulent flows, and we actually have the memory on the computing architectures to do it. Again, to illustrate the power of these high order polynomials, if I get a wiggly function that some of you may have seen me working with lately, you could split it into two parts, two macro elements where I'll fit high order polynomials in. I can fit these high order polynomials through a Lagrange interpolation where you don't really need to know too much, just know that there's coefficient and basis functions for that. And one thing you see there is that you have continuity at the interface between that element. So that's something, if you are a numerics person, you're used to. But what you're probably not used to is that for Lagrange polynomials, you just differentiate the basis functions if you want to get the derivatives. And when I've got that new derivative there, that derivative in the left element and that derivative in the right element, it actually isn't continuous. So we don't have C1 continuity. And so given that these methods are emerging and are appealing for their high resolution, but they do have their limitation, that's something we put to the test. And to do this, we considered a canonical channel flow. You're probably looking at that thinking, why not just use Fourier series in the periodic directions? It's because spectral element methods combine spectral-like convergence of accuracy, but with really appealing geometrical flexibility. So this is a pebble bed reactor, which is about as tough as they come in terms of simulation, and it's handled on 50 billion grid points with spectral element methods. And so we've chosen channels because there's good data to compare with. What did we actually do in this part of my PhD? We ran a bunch of cases where we varied or we tested out high order polynomials and different orders of polynomials. And then we tested kind of increasing the number of those macro elements that you saw in that wiggly function, but fixing the order of the polynomial. So when we tried 5th, 7th, and 11th order polynomials, so getting quite high, we saw that even when we had resolutions that were very, very low resolution, so probably 10 to 20 times less grid points than what you'd expect in a finite differencing simulation, when we considered that simulation, we actually get results that look a lot like a channel flow, right? Like you do see coarseness effects, but this is in effect accurate capture of a channel flow, whereas with finite differencing methods, you'd probably expect it just to blow up. Conversely, we can not change the polynomial order, but we can fix the polynomial order and we can increase the number of macro elements. And in this case, you see convergence to this nice, smooth slice. Okay. We computed a lot of statistics, but I'm just going to skip right up to the turbulence fluctuations. You can see for these very, very low simulations we performed, again, 10 times less grid points than what you'd expect in a finite differencing simulation. You captured the turbulent fluctuations really well. There was a little bit of a underestimate for the peak turbulence intensity. And because that appeared, we're going to investigate why that was actually occurring. Remember, I said that we don't have C1 continuity here, and derivatives explicitly appear in the Navier-Stokes. So we do want to investigate that a little bit more closely. So what we did was we spanned and time averaged the profiles, i.e. you've got periodic directions in this flow. So we've taken slices in the span-wise direction and collapsed it onto one profile. After doing so, we ran that simulation for a long time average. And then this is the resulting slice, right? So not sure how well you can see it from the back row, but at the interface of the macro elements, you actually get this unphysical kick-up. So if you look at this profile, this one's at y plus 15, and I look at my distance, I look at my profile along the free-mice distance, I see these unphysical kick-ups at the interface of the macro elements. But it doesn't affect the statistics too much because it's only a small part of your domain. One way to remedy that is to just use very high-order polynomials. So by the time we went up to 11th order polynomials, that effect was kind of mitigated. Alternatively, you can just increase the number of macro elements where now you just have smoothness, and with further time averaging, you'll see a perfectly straight profile. So one criterion, if you are new to spectral element methods and you want to say, have I got enough resolution? One thing you can do is run your simulation, collect your profiles, and if there's no unphysical kick-ups at the interface of the macro elements, you've probably got enough resolution. Ooh, so I want to see that thing kind of go. Okay. So before, when we had very coarse simulations, yeah, sure, they weren't very satisfying because we don't see that publishable smoothness. But nevertheless, they did kind of capture the overall trend. You did think you were looking at a turbulent channel flow. The derivatives are a totally different story, where when it's a very coarse simulation, you see a field that looks like total garbage. And then as you increase the resolution, you get a proportional increase in the derivative visualization. So to illustrate that neatly, if we take a high order statistic, we take the skewness. If we investigate the skewness of a primitive variable we collected, so the turbulent fluctuations, yeah, we saw a pretty good agreement with the reference data. I'm sorry, I seem to have missed saying that the red line is some high quality reference data we trust, an important detail. So we saw good agreement for all our simulations with the reference data. Okay, there's a little bit of a gain here for the coarsest simulations, but skewness of the derivative quantities was a totally different story where, again, we had total garbage for our coarsest simulations. And it wasn't until we had 10 times more grid points than an equivalent finite difference method that we actually recovered the correct profile. So, okay. So we did compute a lot of statistics and we did do a little bit of maths here in a paper we published where we gave the grid requirements required to capture each of those statistics if you're using spectral element methods. You can see that you get a bunch of statistics for a really cheap price. So you can run a very coarse simulation that's approximately 5 times coarser than a finite differencing method and be sure that these statistics will probably be correct. But if you wanted, for instance, skewness, you needed a very high resolution. So we got a little poem here from our friend Hamlet. Fully resolved or not fully resolved? That is the question. And this part kind of departs from the soliloquy. Resolve the Kolmogorov scale to ensure your simulations will not fail. But what if all you want and dream is the velocity in the free stream? Or if you have a preoccupation with the dissipation, then contain your excitement. So this is the Hamlet again, because doth are the grid requirements. And I don't think doth is correct, but Oh, who knows? Probably just a handful. Okay, so I've kind of extolled the virtues here of NEC 5000 or spectral element methods, but we did actually use a bunch of different methodologies in this PhD. So we were particularly interested in understanding spectral element methods, which is why we've devoted a part of the PhD. We then, in the first particles part of this PhD, we used an in-house author. We wrote in Python, and we compared that with some available software, OpenFOAM, which a lot of us know and love. We then moved back to spectral elements in OpenFOAM, which I'll explain when we get there. But then we GPU accelerate at the end, and this was a lot of fun. These things ran really fast. Okay, so we're moving away now from the single phase flows to particle laden flows. And actually this appeared on JFM today, so that was great, but I didn't get a chance to change it. So if you are now introducing particles into your flows, there's two things you need to know. The first is your Stokes number. So not all particles are created equal. If they're very small, or if the streamline curvature is not too severe, as in this first case, you expect, well, the black line being a fluid streamline, you expect that your particle will be able to trace those motions fairly faithfully, right? However, if you have high curvatures, as we have in turbulence, or if you have kind of largish particles, which, okay, we'll build a bit better definition, but for now, just imagine them as large, they can't follow those motions owing to their inertia, and they show a divergence in their path lines from the fluid path lines. So to quantify that, you compute a relaxation timescale for the particle, where you just input the density and diameter of the particle and kinematic viscosity and density of the fluid. So that gives you your particle relaxation timescale. And then what timescale you choose for the fluid is kind of up to you, depending on what you want to study. But we, in this PhD, tend to focus on the viscous timescale, so on the very smaller scales of the flow. The second thing you need to consider after you've considered what kind of particle you're going to use is how many of them you're interested in. So that's captured here in this volume fraction, where within our problem of interest, we have a volume of the particles. So the volume the particles are occupying in total, and then the corresponding volume of fluid in that domain. Now, if you don't have too many particles, you're in this first part of this map that relates the type of particle, the Stokes number, its timescale, and the volume fraction, so the number of the volume fraction occupied by the particles. You're in this first part of the map where, okay, say you don't have many particles at all, and you have a scenario that looks something like this, which is called one-way coupling. So the motion of the fluid is driving the particles, but there are not enough particles for significant modification of the fluid, right? So we see this forest of eddies that we all know and love, or turbulent structures rather, and we see it looks pretty much like we expect, but with the addition of particles. So the kinds of questions you ask there is, what is the motion of particles and where may they go? You would not focus on what happens to the turbulence, simply because there's not enough of an effect. If you say, okay, I actually want to throw more particles into my domain, you're now in the two-way coupling region. So now you have so many particles that your turbulence is actually being modified. In this case, it looks like it's kind of been killed altogether. But I should point out that depending on the type of particle you use, you could actually enhance turbulence. So you could create more turbulence in the wakes of the particles. If you then were to include more particles still, and this is just for your own knowledge, it's not something we consider in this PhD, it would be collisions of those particles that are additional phenomena you need to capture. So this is a visualization that I actually used in my confirmation. I didn't have enough time to make a better one. But this is the motion of particles in a pipe flow, and the flow is out of the page. And it kind of looks like the sun, right? To me. But I hope you can see that the motion of these particles is non-trivial, right? So we don't just have uniform dispersion, and it's not a boring problem. There are kind of streaks forming, and you can see depletion as time goes on of particles. So there is a bit to study here. But what we're considering in this part of the talk, we're considering the motion of particles, and these results are relevant when you don't have too many particles. So when pipe flows are driving the motion of particles, but the turbulence itself is not affected. In that case, your governing equations for the fluid phase are the Navier-Stokes with this interphase coupling term. But because we're arguing there's not many particles and the turbulence is not affected, you just kill it, so it's zero. That's not a modeling assumption, that's just an observation that you don't have many particles, so you really don't expect the turbulence to be affected. But then you have to, so if you want to do this at home, and you've got a Navier-Stokes solver that you dust off every night, and you want to add particles to it, you would time march your Navier-Stokes as you do every day of the week. But now that physics wouldn't be changed at all, but you'd introduce many of these infinitesimal points that represent a particle, and you'd solve the corresponding ODEs where, importantly, this is your Newton's second law, and it's the forces you choose to include there that drive the dynamics of the particles, right? So this is the all-important step where you choose what forces you're going to include. And at each time step, you interpolate the velocity from your Eulerian mesh for the fluid onto an infinitesimal point for the particle. That particle will have an existing velocity, and so the slip velocity computes the drag force. And as you can imagine, if you're considering, say, snowflakes rather than spheres, you'd have a different drag correlation here to drive different dynamics. You also take the Lamb vector, so you interpolate the vorticity from the fluid, and that's going to give you a lift force, which we'll get to in a moment. But you also need to consider when particles impinge on a wall, do they stick there or do they rebound and re-entrain into the flow? As I said, the important thing to consider in the actual setup of these simulations is the forces you include. So I think the drag force is something that we've all kind of thought about in the past, where if you have a cylinder, for instance, there's a relative motion of the fluid past it, and you get viscous and pressure drag. So that's all captured. That's all captured by a slip velocity that drives the drag force. But additionally, in shear flows, you have this important lift force where, because we're modeling the particle as an infinitesimal point, but in reality has finite size, you have an uneven distribution of fast flowing motion above the particle and a low speed motion below the particle. And that creates something analogous to a Magnus lift force where those particles migrate in shear directions. So particularly if you ever consider laminar flows, this force is actually all important. And there's some really nice work by Safdie on that. Okay, so I pinched Javier Jimenez's picture of turbulence here, where he has many, many scales to illustrate what kind of particles we consider. And I think I'm repeating it to people who already know, but you got this separation of energy-containing eddies to the small Kolmogorov scales that dissipate the energy. So this is the kind of scales and motions you expect to see in the turbulent flow. But we're not considering quite such scale separated flows. We've got a more modest scale separation in the simulations we perform, but the particles we consider are smaller still, so they're sub-Kolmogorov. And that's driven by kind of what you can do. Modeling or simulations of particles larger than the Kolmogorov scale are quite difficult. So we consider 4 classes of particles here, where we've normalized their relaxation timescales by the viscous timescale. So point 1, we have particles that are small, have relaxation timescales faster than the viscous scale. So we expect them to trace all motions. On the other end of the spectrum, we've got large ballistic motions that are large ballistic particles that are going to filter high frequency events. And as Katie pointed out to me, I didn't stress where the application is in my flow, but in a pandemic, you see that there's a wide range of droplets following those coughs. So this person has coughed, and you can see these large kind of mucus droplets, and they would be modeled by these ballistic Stokes plus 100 particles. But it's hard to say, but you have very tiny fine particles, which form kind of like a spray, and those particles will be more adequately modeled by these smaller Stokes plus equals 0.1 particles. So what did we actually study here? So there's a bunch of literature that's in channels, primarily in DNS group. So we see Moyne's group, Luca Brandt's group, and Luca Brandt's group again, where they're considering accumulation of particles at the walls. So that's to say that, that's called turbophoresis in the literature. It's primarily in channels. And so that's the observation that if you have a bunch of quite small particles or low Stokes plus number particles, now that you know what that is, you would expect a uniform concentration between walls. As you increase that Stokes plus number though, you see concentration spikes forming at the walls. So to see if that was something real, we wrote our own in-house Python code just as an excuse to learn about numerics really, but we'll say it's to validate OpenFOAM, to make sure OpenFOAM's real. So we wrote this doubly Fourier, oh no, it was Fourier in one direction, finite volume in the other directions code on Python. And we checked and we said, yep, we've got real turbulence by comparing to high quality data. We then added a dispersed phase, the particles, and compared the output to OpenFOAM. So when we considered small Stokes plus equals 1 particles at 2 time instances, so 1 physical second and 10 physical seconds, we're just thinking of this as a non-equilibrium problem. At this part of the study, we didn't really worry too much about what those time intervals mean. Yeah, we saw no accumulation, no more normal accumulation in our Python output, nor in our OpenFOAM output. So when we went to Stokes plus 10, we saw that at 2 separate time instances, we saw increasing concentration spikes near wall in the OpenFOAM data, and our solver agreed with that perfectly. So we do trust our OpenFOAM data that here is in channels, but in the analysis part of this study is in pipes. So what is turbophoresis really, and how do we motivate what we were doing here? If I consider a cloud of particles in a wall flow, so if I consider that cloud of particles and I set up, it's just not working. Okay, a concentration gradient. If I set up a concentration gradient in isotropic turbulence, and I think this is a problem that's kind of old news. We all know about Fickian diffusion. But because of those concentration gradients, we're going to get a flux across this surface that I've just artificially set up. And that flux is adequately modeled by a concentration gradient, where X is arbitrary here, and diffusivity constant. Okay, come on. Sorry, there's another thing appearing. Okay. But what about in wall turbulence? So in wall turbulence here, I haven't set up any concentration gradient. But as we know, the difference from isotropic turbulence is that we now have gradients in our turbulence. Please work. Ugh.
Too much animation. All you want to do so
It worked yesterday. Okay, wait, let's give it one more second. This is awkward. Okay, as we all saw, that worked smoothly. So we had fluxes in the absence of a concentration gradient. Fluxes in the absence of concentration gradient tell me, hey, this flux expression is old news. It's indeed old news. It doesn't work anymore. So if we want to model the fluxes in our wall flow, we're going to need additional terms. So to summarize the DNS data that's been collected by various groups here, they work in channels. They toggle what happens to particles when they collide with the wall, and they toggle whether or not they include the Saffman lift force. This has received a lot of attention from analytical communities, where they made different arguments on what's driving those fluxes in wall flows, so those non-concentration gradient-driven fluxes. And they always rely on this expression that there is some diffusivity parameter associated with concentration gradients, but there's also this additional diffusivity parameter just associated with the local concentration. So we tried to develop a method to see what are the true values there. Where do these values come from? And is this really a complete description for the concentration? Does it satisfy a continuity equation? To do that, we conducted 5 simulation sets in channels. This 5th one was just toggling the density of the particles, but otherwise we toggled which forces we included on the particle, and we toggled what kind of walls we were considering. So the particle wall interaction was toggled. And we first kind of commenced the study by looking at all the turbulence statistics. And one thing we learned straight away was these darkest markers corresponding to Stokes plus 100 particles, they had a real strong divergence from the local fluid phenomena. So in grey, you see fluid profiles. They're sometimes a bit obscured, but you see that, okay, there seems to be a simple connection between Stokes plus 0.1, 1 and 10 particles and the underlying fluid. But for Stokes plus 100 particles, something different is going on. And that's because they retain their inertia for a lot longer. It's not shown today, but that motivated a lot of Lagrangian correlation modeling. where we kind of argue what kind of effects you might need to incorporate for Eulerian-based models of particles. Okay, so that was just a quick kind of glance at the turbulence statistics we looked at. But what we were really interested in is measuring this turbophoresis effect. So in the simplest case, if you had absorbing walls when our simulation progressed in time, if a particle's radius came into collision with the wall, then we modeled that as sticking onto the wall, and that fed into this transfer flux onto the wall term, which we then normalized by the bulk concentration of the particles and viscous or friction velocity of the fluid. So this has been done in experiments by Liu and Agarwal, and that's in these black hollow circles where they're considered olive oil droplets, I think, in glass columns. And there are eddy viscosity models here in blue by Abdit Guha from Cambridge in 1997. But our 4 simulation sets reveal that up until about Stokes plus 10, these models work well. And afterwards, if you're considering larger Stokes plus 100 particles, well, if you have rebounding elastic walls, you have a big kind of gap between the data we collected and the experimental results. So in future, mathematicians, I guess, will need to build separate models for rebounding particles. Okay, so there is something else we saw, which was nice, which was termed preferential concentration. So we are primarily interested in accumulation of these particles at the wall, but if I progress these slices, these streamwise or normal slices of the fluid in time, what I see is that I've plotted background streamwise vorticity, and these high intensity streamwise vorticity events actually cause particles to flee that region. So yes, particles that are Stokes plus 10 or 100 accumulated at the wall, but also in the cross section, you had an uneven distribution because particles of intermediate timescale fled the high vorticity regions. And I just thought that was kind of pretty. Okay, so what we really wanted to do was model this wall accumulation that was occurring. And to model that wall accumulation, we got our DNS data and we said, hey, you can actually measure each of these terms. You can measure the flux when you take 2 subsequent snapshots of the particles in your flow. You can then measure what the concentration gradient was, and you can measure what the concentration was. And then you can just divide through by C, the concentration, to generate a linear equation. And when you plot individual realizations of your flow, you can just regress a line of best fit, and that intercept is actually your turbophoretic part, and the slope is your gradient-driven diffusion part. We then compared these 2 coefficients we determined, D1 and D2, with the eddy viscosity model of Guha. There's a lot going on, but in D1, when we considered that turbulence part, these grey lines are the model of Guha, and you can see our data kind of fell on top of Guha's data pretty well for all values up until Stokes plus 10 and inclusive. But that phenomena broke down when you considered these larger ballistic particles, and our gradient-driven diffusion really did not match the results of Guha, and that's something I think for future PhDs to consider. But after we got our profiles for D2 and D1, we wanted to see how much can you trust them, how much is that a true model for the flux, and you can ignore this decomposition for now. Sticking to this continuity equation, we kind of argued, well, if you plug in those expressions for the flux into the continuity equation and time march that continuity equation, then you see what your model prediction is for the concentration. So we did that. We set up a 1D domain with our 1D fluxes, and our boundary conditions were no flux through the wall and no concentration gradient at the center line. And you can see that our red marker data from our simulation, which shows wall normal concentration profiles of particles initially from uniform, had depletion with time increasing. And we caught that pretty much perfectly with our model, right? So you see this depletion in the center line is really good. But further than that, you can then decompose those flux terms to see what's driving that near wall accumulation. And actually what we found that when you increase the size of the particles to Stokes plus 10, it was this kick up in the derivative of the turbulence term that caused all that accumulation. Up until this part, what we've done is we've kind of taken 3D phenomena and tried to project it onto a 1D model. But we're just going to take a quick look at what the 3D mechanisms were that were really driving those transfer of particles. So if I consider the 3D structures in the flow, so the Q2 ejections. So for those of you who don't know, these are correlated motions that are moving away from the wall and go back towards the center line of a wall flow, and they transfer momentum. If I plot contours of those and my particles that are actually fleeing the near wall region, this is taken at y+15, I see a pretty good correlation. So transfer of the particles is intimately driven by momentum transfer structures in the fluid. And this was true in the other direction as well, when we considered the turbulent sweeps which were wallward. Those momentum structures of the fluid were what was driving the particle migration as well. So that's some summary there for that part of the talk. No poem this time. Turbophoresis, we captured it by a flux decomposition model. We plugged into our, continuity equation, but expand into convection diffusion. And it did reproduce the particle concentration. We didn't really touch on this as much, but those 3D mechanisms that work for Stokes plus 10 in transferring the particles broke down. And sometimes because of their sufficient inertia, larger particles could decorrelate from the 3D structures of the flow. So we're going to take a fast look at the next part. So there's 4 parts, but they each get shorter. So what we're going to consider now is what happens when you increase that volume fraction, and now the turbulence itself is modulated. And this is ostensibly a more interesting problem than what we just saw, but it's also a more difficult problem to capture. If you want to capture it really well and you want to be sure that your simulations are going to be famous, what you could do is have supermassive or super well-resolved grids and use an immersed boundary method for the particle where you resolve the individual forces on the surface of the particle. But Luca Brandt, who evidently has huge computers, conducts friction Reynolds number 180. So that's pretty modest, something you can do on your laptop for a single phase flow. So 13 billion grid points, right? So that's huge. But the kinds of models we're doing today, point particle models, are 125 times cheaper. And I should say they are quite ethical, I guess, in their computing time, in that they do state that the purpose of these grid resolve methods is to drive better modeling for those efficient methods. So that's not really good for the environment to run too many of those. So before we killed this interphase coupling term, that feedback force. So when you compute a slip velocity that's going to drive a drag and lift force of the particles, that's a momentum transfer. And that momentum that's being gained by the particle phase is lost by the fluid phase, and vice versa if the particle is decelerating. So the thing is that you can interpolate your fluid quantities onto local infinitesimal particle positions. You can do that, and that's quite a straightforward interpolation. But once you compute a quantity then for that interphase coupling term, the question is, how do you give it back to your Eulerian mesh? So when we use NEC 5000 in spectral element coupling, we actually use the Gaussian projection kernel. And when we use finite volume coupling, finite volume method, not coupling. Okay, fine, coupling. We just smeared that out and distributed it along the local control volume. On left here, we have an interphase coupling visualization at a reference height for OpenFOAM, where you can see small spikes in the local cell or control volume in your simulation. On the right, you have the spectral element Gaussian kernel, where you can see the values are smoother. We weren't really too sure what's the appropriate way to couple these phases, which is why we did both methodologies. But what we found was that you had really good agreement in the statistics, whichever methodology you use. So the streamwise interphase coupling was pretty much perfect for OpenFOAM and NEC 5000. And correspondingly, close to the wall, you have turbulence attenuation in these cases, and the level of turbulence attenuation was perfect as well. One more thing to say, we ran a lot of simulations in this part of the PhD, where we considered 3 Stokes plus values, 50, 100, and 500. We varied the volume fraction to have a corresponding different effect on the fluid. We ran that in channels and pipes, so that was kind of inspired by Professor Monti to see how similar those canonical flows would be in particles. But these simulations, even at friction Reynolds number 180, are actually really expensive, right? So as you can imagine, when your pressure Poisson solver works really hard for numerics people, you've now got additional sub-Kolmogorov scales that the iterative solver needs to solve for. And so these simulations, mainly due to the kick up in the pressure Poisson solver time, are 20 times more expensive than single phase flows. So just a few brief results. So we showed those concentration spikes occurring in the previous part of this talk. And those concentration spikes, so we'll just focus on Stokes plus 50 particles in pipes here, were actually augmented when the volume fraction was increased. And you saw radical changes in the turbulence. So here's my unladen forest of structures in a pipe. And as I increase the volume fraction, I correspondingly see a depletion of those structures. So you've got this kind of almost quasi-laminar state appearing with increased particle loading. If I take a reference height, a reference law normal slice, and I have a low loading, which is these three parts here, I see my classical streak spacing of about 100 plus units, but you see that those streaks look altogether different for a higher loading where they look really smudged out, nothing like the unladen case anymore. I think we did investigate which structures were most affected, and that tended to be close to the wall. There's intermediate structures, so there's missing energy here with increased loading compared to the low loading case. I think I'll kind of gloss over that. So some of the summary here is that turbophoresis was actually enhanced by the presence. Turbophoresis effect was enhanced by higher volume fractions. We saw a modulation of turbulent length scales. So when we looked at our spectra, not all scales were being attenuated. Some were preserved and others were depleted. And we would conclude that larger long wavelengths were least affected by the presence of particles. So just very quickly, this is the last part of PhD, only 3 slides. So, no, this joke kind of failed, but so a lot of us want to grow our super, and that's why we're all university people, got great super. But, you know, in a way, computing time is just like money. And if you're on CPUs, you've got an average retail super fund. But if you're on GPUs, your compute time is going through the roof. These things are really awesome. So, yeah, I guess maybe I work for NVIDIA or something. And we got interested in GPUs because, you know, basically it was Jin, to his credit, who I'm not sure if he's here, but Jin started saying that these things were super fast. And I think I looked up the Spartan schedule and said, if you tally up all the CPUs on Spartan and they gave them all to you, which you know you've got no chance of receiving that much allocation, you would get 448 double precision teraflops. On the other hand, if you use the GPUs, you've got 29 of these nodes, you've got 4 units per node. You actually have more than double the computing power on the GPUs and the CPUs. So we always call them accelerators. But I think the wise Scott Morrison would call them essential workers. They're really powerful. And on the left, I guess, is an example of the kind of simulations we performed on CPUs. But personally, on our budgets, we went to much, much higher grid resolutions and much higher friction Reynolds number on the GPUs. And just to conclude, this part of PhD, we actually considered Taylor dispersion. So we looked at what happens when you have this initial disk of particles and the rate of spreading for that phenomena. Computed some longitudinal dispersion coefficients, some inverse Peclet numbers, and yeah, found a Reynolds number dependence. At this point, I'd like to conclude. I'd like to thank Andrew. Andrew's sometimes been helpful. And Jimmy, who you know never gave up on me, and I think I'll always be really touched by that. And like to shout out to Leon, so give him a crown. You know, the faculty, they always get the adulation. Everyone says what a great guy, I guess Nick is. Andrew, not sure. But no, it's true. You know, people like Leon, I can honestly say, help. Postdocs just help so much at particularly the first year of your PhD. And he really sets a very high, excellent standard for our group. And thanks a lot, Leon. Without you, I don't think I would have been here. Okay, thanks everyone. That's it. Happy to take hard questions, no easy questions.
Any questions for me? No questions?
Oh, yeah.
You show us the spectra again.
If it was anyone else, I'll say no. If it was anyone else, no. Yeah. Yeah. But Yi Cheng, you had a question?
Yeah.
Okay. Oh, yeah.
What's the question, Tom? I have no questions. Just one. We just want to look at.
Yeah.
Trying to understand what you're plotting.
Yeah, so I skipped over it. So we mainly were interested in how channels are connected with pipes, whether the turbulence modulation was the same in both geometries. And yeah, we had pretty good agreement really. But you also see, so these contours are basically not affected, and these contours are affected, and you see that there's missing energy up to about y plus 15 with intermediate wavelengths. So those larger wavelengths were not really affected.
But you don't have very large structures.
No, we can't afford them. Still trying to grow our super.
You can't make a joke.
I'm trying.
But you can't.
Yeah. I'll say,
The value is the concentration of the
yeah. Yeah.
And I'm wondering if the collision between the particle influence the
Yeah.
concentration.
Yeah. So because you see those concentration spikes is why here you see more depletion of energy structures, right? Whereas I guess if you chose a different class of particles that tends to reside in the middle of your pipe, you'd expect those structures. So it's kind of interesting because we always think of fluids problems as boundary value problems and like rough wall problems and so forth and so on. But particles are different in that they can modulate other parts of the flow. So, yeah. Yeah.
Did you neglect gravities?
Yeah, we did. So we did, but actually has a big effect.
Only you did, not in general.
Yeah, it was all me. Now, so we neglected gravity, but it turns out that so we kind of started off making the argument that these are vertical pipes. So because they're vertical pipes, we were arguing gravity will just drive it in the streamwise direction. You don't really care. But actually, even then, gravity has a big role, which we recently learned. But yeah. No, yeah, you're right. It is a limitation, that's for sure.
Because your Stokes number,
yeah, it's large.
It's not enough to fully describe your physics.
Yeah, I agree. Yeah, we should include the gravity in future and.
I think density ratio.
Yeah.
It's not right.
Yeah. No, okay. So we do mention the density ratio we use. So we are using 1 point there in the 2D map, but you are right. It's a whole separate study to understand density effects, which is actually what the reviewer asked us, which is why we included that higher density simulation as well. And for smaller particles, it wasn't a big deal, but yeah, for Stokes plus 100 particles, it was a big deal. So,
yeah. So you basically say that Stokes is higher and deviating to. Did you agree with that?
Yeah.
But so
Mm.
which you force.
Mm-hmm.
You're just like rotating local or just flowing around.
No, we neglected it, but yeah, it is another.
How can you think that this?
For larger particles,
Yeah.
large, yeah. Um, yeah, maybe that's something we can do together. Okay, any other
Maybe you
questions?
should think about postponing submission of the PhD thesis.
I could just start another one. Yeah. Yeah.
I was interested in the slide just prior to this one. Can you talk me through what's happening there? So the color contours are
Oh yeah, yeah.
streamlined velocity fluctuation.
Yeah, that's right. Probably. Yeah, this is all at y plus 15, so that's a bit misleading. That should be a little bit higher.
Yeah.
Yeah, it's all at y plus 15. This case here is your Stokes plus 500 case, which for a given volume fraction means there's not many, which means that this is our best estimate of these slices for an unladen flow. Okay, so the turbulent fluctuations, streamwise turbulent fluctuations in an unladen flow at y plus 15. So correspondingly, when you increase particles, you've got, or particle loading, you expect more effect on those turbulent fluctuations. And for our Stokes plus 500 particles, which is this bottom row, you didn't really see much modification of their structures. And that's just because for a given volume fraction, if your particles are larger, then you need less particles to make up that volume. And so there just weren't enough particles to really modulate the structures. But so these are our Stokes plus 100 particles row, where, yeah, lowest, mid, and high volume fraction of particles. And it's kind of interesting to me because, okay, so if we focus on the Stokes plus 50 particles, you have these streaks of particles that are settling in low speed streaks. So they're forming long streaks of particles, but actually this was kind of enhanced, I think, when you increase the volume fraction. So you had more dense packing in the low speed streaks.
It looks like those streaks are stabilized.
Yeah, yeah, yeah. Yeah, for larger particles, they can be really long. They can span almost our whole domain, which is.
Yeah.
Okay.
Any other questions?
All right, if not, then can you join me in thanking me?
Oh, thank you.
Thanks.
Yeah.
You're submitting your thesis today, right?
No, probably next week.
Oh, okay.
I just wait. How do I end the recording?